Hey everybody. So this for my first section, y'all missed yesterday, and this was the bell ringer. Oh wow. When I changed this to convert to text, it did not bring the R in with it. So I did that to make it kind of easier to read because my handwriting can get a little bit messy. But, this isn't about necessarily doing it right now. If you would like to do it, you could have done that right there at student.desmos.com. But if I have two boxes and each box has the same number of pencils and then I add 3 pencils just to the left box, well, they have the same number of pencils. So the reason I asked this question is because when we're looking at boxes and we're imagining having the same number in each box, we don't want to just make the claim that they're equivalent by adding more pencils to one box and not the other. We intuitively understand that you have to add the same thing to both boxes to make them remain equal. But when we get to equations, sometimes we forget that. So when you have an equation, you have some stuff equaling some stuff. The left side might look different than the right side, but that's usually because there's some sort of variable there. So 2x plus 1 equals 13. In a case like this, the left side is still equal to 13. It is 13. It's just written differently. We just have this as an unknown. But no matter what, that left side has to be the same thing as the right side. So when I have the second part of the bell ringer, if I have two equations and each side looks different but represents the same number, and then I add 3 to just the left side, will they be equal? No. Because I'm adding, when the equation sits like this, we assume that it's true. We assume that the left and the right side are the same thing, just written differently. So if we change just the left side without changing the right side the same amount, then obviously we've broken our equation. So we've made it a non-equivalent equation. So I'm going to model a few things about solving these and talk about what we need. So the first one I'm going to do is a relatively easy one. It's a one-stepper. So when I'm looking at this thing, I have 1x, so some unknown number minus 5, and that is allegedly equal to 27. So some unknown number minus 25 is equal to 27. For things this easy, we can probably just say, well, it's 32. 32 minus 5 is equal to 27. There's only one answer. But for more complex ones, we don't want to plug and chug because we could be sitting there for an hour trying to figure out the right number and may still not get the right number. So in this case, I want to kind of come up with a way to solve and have it tell the equation itself, basically making new equivalent equations, that where this is equal to something, so I know exactly what x has to be. And that's the whole point of solving an equation. So in this case right here, I have some unknown number, minus 5. Well, I don't want that minus 5 there. I want it to just be x equals a number. So what I'm going to do is I'm going to undo this minus 5 part, or undo this adding of negative 5. And by doing that, I'm going to add a positive 5 to both sides. And again, I can't just add to one side, because it's like putting 5 things into the left box but not the right. So when I look at this thing, I like doing it on the same line. You can do it below in this little notational space that doesn't actually exist, but that confuses students sometimes. So I know I'm adding 5 to both sides of the equation. I don't need to do it below. That area doesn't exist. But sometimes it's helpful for notation. So I look at this and I say, all right, on the left, simplifying, I have x. Minus 5 plus 5 is 0. So I'm not going to write this usually because it's the additive identity, so it doesn't do anything when you add or subtract 0. But I'm just going to put it there for good measure for right now. 27 plus 5 is 32. And realizing that adding 0 does nothing because it's the additive identity, I realize that x has to be 32. But Mr. X, how do I know that it is 100% true? Well, number one, you maintained algebraic equivalence by adding or subtracting the same thing from both sides. But either way, we can go ahead and plug this in for our x. Whenever we do this, it replaces our x. Nothing else changes. I'm just replacing what I am saying is my solution. This is the solution. Remember, a solution is a value for your variable that makes your statement true or makes an equation true. So instead of writing x, I'll write 32. And everything else will be the same. And then I can do the arithmetic on this and say 32 minus 5 is 27 equals 27. This checks out. That is a true statement. So when you're replacing this, a question I've gotten a few times is, hey, how come the final answer didn't equal 32? Well, that's a good question. That's not our goal. Our goal when we plug it in to confirm our solution is to check to see if the left and the right side are equal. If they are, then we know it's a true statement. We know 27 is equal to 27, and if that comes out that way, then we know it's a solution to our equation. It has made an always true statement. Now, if you had gotten something a little different, like if you had gotten x equals 0 or something, I don't know how you would do that, but then you would have gotten negative 5 equals 27, which is not a true statement. Any other number, try plugging in other numbers that are not solutions. You will get an inconsistent equation. You will get a false statement, something like negative 5 equals 27 or 0 equals 27, something like that. So I want to go over this example because this is a common mistake students make. So remember, when I am solving equations, I need to do the same thing to both sides. Of those things that I can do, I can add a constant or anything. I can add or subtract from both sides. That's one thing that I can do to maintain algebraic equivalence. That means that the new equation is equivalent, is the same thing algebraically or in structure. I can multiply or divide. Well, I'm going to do these separately. I can multiply by a constant. I can multiply by a constant. Note, I'm not saying I can multiply by a variable. If I multiply by a variable, we're going to talk about it a little bit later, it kind of changes our solution set. But multiplying by a constant or just a number. So like 5, negative 2, 1.555. Pi. Basically, something that is just a constant number. I can also divide by a non-zero constant or a non-zero number. So I say a non-zero number because dividing by 0 is not defined. You cannot divide by 0. It does not make sense when you think about it. If you take a piece of paper and divide it into one piece, then each piece of paper is one piece of paper big. If you divide it into a million pieces, each piece of paper, each one of the things that you divided it by, are a millionth of a piece of paper big. But if you divide it into 0 pieces, it doesn't make any sense. A lot of students try to say it equals 0, but that's not true. Basically, as you approach dividing by 0, it gets bigger. Each piece of paper gets smaller and smaller and smaller, but the amount of them approaches infinity. So it ends up being undefined. So let's look at this. The most common mistake here is when students see this. One big thing that students don't understand is we want to isolate x. So we're not going to mess with x here. We want to get rid of this negative 2. And when I look at this, I say, what is negative 2 currently doing to x? That way I can undo it by doing the opposite. Well, when negative 2 or any number is sitting on top of a variable as such, it is implied to be multiplying. And the opposite of multiplication is division. so I can divide both sides by -2. The most common mistake students do here is they make a mistake and accidentally do that. They divide both sides by 2, they cancel some stuff, and they mess up their signs. You want to divide by the entire coefficient. If you're ever subtracting your this term, or you are adding a negative number times x, you're going to divide by the entire coefficient. That way, your -1 will cancel and your 2 will cancel. Otherwise, you'll mess up your sign. So then I get 20 divided by -2. So they're opposite signs being divided. So I get a -10. If you hadn't done that and you divided both sides by just 2, you would have gotten x equals 10, which would have not solved it. But Mr. X, how do I know? Let's try this one. The actual answer I'm saying is true, and plugging that in for x into our original equation, I get, that stays the same, and then I get negative times a negative is a positive, so I get positive 20 equals 20, which does check out. That is a confirmed solution. But watch what happens if you do the common goof, and instead of dividing by -2, you divide by just 2. A lot of students do this, and they just assume that that's fine, and then they get x equals positive 10. Well, plugging that into the original equation, -2 times positive 10. Nothing else changes about the original blue equation right there, and I get -20 equals 20. Some students will say, yeah, this works great, but it's not. This is a -20, and that is a 20. If you take the number line, here's 0, here's 10, here's 20, here's -10, here's -20. You realize one of those numbers is right here, and one of those numbers is right here. There's a difference of 40 units between those. So that doesn't work. The only thing that you can possibly do, the only the only quantity that x can equal in this case to make that equation true is -10. Let's look at this one. This one can be as hard as you want it to be. I see that 3/4, and I immediately know what to do with it, but that's because I understand how to use the reciprocal. The reciprocal is just flipping over a fraction. That's it. That is the multiplicative inverse. If I multiply a number by its multiplicative inverse, I get 1. So let's try an example. 1/17. If I multiply by flipping this over, and I multiply by 17 over 1, I get 17 over 17, which is equal to 1. It doesn't matter what these numbers are. If this was a 4 and this was a 4, the 4s would cancel. Basically, I'd have something that looked like this. The 4 over 4 is 1. The 17 over 17 is 1. No matter what happens, if I multiply a number by its reciprocal, or if I multiply a number by a multiplicative inverse, I always get 1. Mr. X, how do I do that if it's just a number that's not a fraction? Well, put it over 1. That's my alarm. Gotta get up. 2 over 1. Then I can multiply by the reciprocal, and I get my 2's cancel, my 1's. Well, you might say that they cancel, but I kind of want them there, and it's going to equal 1. Now, how does this help us? Remember, my goal is to have x by itself equal to a number. But remember, just x by itself has a coefficient of 1. So I want to turn this into a 1 somehow. Well, I know how to do that the easy way, and that's multiplying by the reciprocal of it. So I can multiply by 4 over 3 on both sides. And if I do that, on my left side, I get 12 over 12x. And on my right side, you might say, how do I multiply a whole number by a fraction? Put it over 1, top times top, over bottom times bottom. 12 divided by 12 is 1, so I get 1x here, and I never write my 1. And I get my answer as 8/3. Okay, well, that's all fine and dandy. But what if you didn't want to do it that way? What if you didn't think of the reciprocal in the heat of the moment? Well, that's simple. You can do it in 2 steps instead. So I see that denominator of 4, and I want to get rid of a denominator. If I'm dividing by a number, this 4, then I just multiply by that number to get rid of it. So I'll multiply by 4 on both sides. But Mr. X, how do I do the whole number times a fraction? Same thing as before. Put it over 1, top times top, bottom times bottom. And on the right, I get 8. Okay, 12 divided by 4 is 3. And then I say, all right, I'm multiplying by 3, so I'm going to divide both sides by 3. The 3's cancel because they become 1 again. 3 over 3 is 1. My coefficient's now 1, so it doesn't do anything. And I get x equals 8/3. It's the same thing, so nothing has changed. I'm sure you can make this more steps than that, but it'll be okay. You don't really need to. It says, don't forget to confirm your solutions. I did that earlier in class on the fraction, and I don't feel like it's pedagogically relevant for the amount of time it'll take for this video. If you want to, you can go plug that in. Let's try a spicy one. Not super spicy, but it's got a couple of mistakes students make. One of the biggest things that students have an issue with is they see a fraction and they shut down. Well, me, I don't. I look at that and I say, well, I have a variable term minus 1/17, which is just a number. So, to get rid of that negative 1/17, I'm going to add 1/17 on both sides. Well, on the left side, I have negative x minus 1/17 plus 1/17 is 0, so it disappears, it cancels. And on the right side, I have 9/17 plus 1/17 is 10/17. That's really all there is to it. A lot of students don't realize that when you have the same denominator, you just add the numerators or subtract them, whatever you're doing with adding and subtracting. Oh, this is where students usually stop and they say x is equal to 10/17, but we've got this negative here. It's implied to have a -1 coefficient. So there's 2 ways that I can deal with a -1 coefficient. I can either divide both sides by a -1 or multiply by -1. -1 is one of those special numbers where it doesn't matter which one you do. So I'm going to, for ease of my brain, I'm going to multiply both sides by -1. -1 times -1 is +1, so it cancels. You can try it out by dividing by -1 or multiplying 1 over -1. It doesn't matter. It's just the fact that this is a fraction I didn't want to divide in this moment. It only works with -1. So I get negative 10/17. And that's my final answer. That reminds me, anytime we divide, say I have something like -2x equals 4. Anytime, your first instinct is to divide both sides by -2. And you'll get this equals -2. All right, I'll put that over here. That one's an easy one once you practice it. But I'm going to tell you, there's actually another way to think about it, and it works the same way as the reciprocal. You can express -2 as -2 over 1. And then you can use 1 over -2 on both sides. And then I get, on the left side, I get -2 over -2, which is the same thing as if I had divided. And I get just x. And on the right side, I get 4 over 1 times 1, 4 over 1 times 1 over -2. And so I get -2. So effectively, I get 4 divided by -2 still. The reason that this is important is when you're dealing with fractions or other types of weird-looking things, sometimes multiplying by the reciprocal is easier than dividing by a number. And this will be the last example I do for right now, because it's the same idea. This one's a two-stepper. I look at that and I say I have a variable term where my x is. I want to get it by itself. So I'm subtracting 1/7. So let's go ahead and add 1/7 to both sides. Kind of messed up my plurals there. Negative 2x. Negative 1/7 plus 1/7 is 0. So 13/7 plus 1/7. So 13/7 plus 1/7 is 14/7. It might be a good time to simplify that right side to make it not look like a fraction. 14/7 is 2, and then I can divide both sides by -2, or multiply both sides by 1/2. It doesn't matter. X equals 2/2 is -1. Hopefully this helps.